Welcome back to statistics. Many, if not most, of the problems that we're interested in real life have to do with relationships. In statistics, that means relationships among variables. So, for instance, I might be interested in the relationship between political affiliation, say Republican, Democratic, or Independent, and educational level, say high school, no college, college, graduate degree, that kind of thing. And those kind of questions can be addressed using various techniques in statistics. The techniques you use depend on the kind of data that you're dealing with. In the example of political affiliation and educational level, both those variables are categorical. What we're going to talk about today and over the next several videos is a method called linear regression for exploring the relationships between quantitative variables. And we'll see that this can be done in a very nice way. We can quantify the relationship, we can measure its strength and its direction, we can use it to make predictions about the variables, among other things. And so, what's it all about? Let's check it out. So, introducing linear regression. As I said, linear regression is about relating to quantitative variables. There are other techniques that are used when you're relating categorical variables, or maybe a categorical variable and a quantitative variable. But linear regression is all about relating to quantitative variables. And as usual, I'd like to start with an example. Um, this is data that I've collected over the course of my career teaching stats. I've presented students with an exercise in which they basically make as many hash marks as they can just using pencil and paper in 30 seconds. And then I ask the students to do the problem again, to do the exercise again, but switching hands. So what students will have done is they have made one set of hash marks with their dominant hand. Uh, that would mean the right hand if you're right-handed, or the left hand if you're left-handed. And then the second set of marks is made with the other hand. And I've recorded the data from a recent semester, and there were 40 students that I had in my stats classes. And for each student, I recorded the number of hash marks they were able to make in 30 seconds using the dominant hand and using the other hand. And there you see a little piece of that data set right there. So the first thing to notice is that this is bivariate data, right? For each individual, we've recorded two variables: the amount of hash marks they were able to make with their dominant hand and the amount of hash marks they were able to make with their other hand. And linear regression is all about the relationships between two quantitative variables. So bivariate quantitative data. There's a lot of questions we could ask about this. What is the relationship between those two variables? How can we describe and visualize that relationship? And can the number of hash marks made by the dominant hand be used to predict, in some sense, the number of hash marks made by the other hand? We're going to be working with a distinction we made some time ago in bivariate data, and that's between an explanatory variable and a response variable. That'll be important in linear regression. Recall that an explanatory variable is one in which we have some sort of a priori knowledge that it may be causing or at least affecting values of the other variable, which we call the response variable. So in this example, we're going to consider the dominant hand variable to be the explanatory variable and the other hand variable to be the response variable. So how can we visualize the relationship between these two variables? Well, for quantitative variables, a scatter plot can be used to visualize the relationship. Here you see the scatter plot for our dominant hand data, dominant and other hand data. And a scatter plot is simply a point plot of the data values. For each individual, the explanatory variable provides the x coordinate and the response variable provides the y coordinate. And so by looking at the x and y coordinates of each dot in the scatter plot, you could see the values of the explanatory and response variables as the x and y coordinates. So you can just read the graph essentially. If you read it very carefully, you could reconstruct the data values from the graph alone. In describing a relationship, there are three main aspects to the pattern that we want to describe. First is the form of the relationship. Is the relationship linear versus nonlinear or curved? And there you want to imagine sort of the trend in the data. For our dominant hand data, we can see that you can imagine a linear trend line sort of in your mind's eye describing this data. Uh, it would be a line in this case that would have a fairly shallow positive slope, right? Going from the lower left to the upper right. It would kind of just go right through the middle of that scatter plot that you see. So this would be a linear association. The form of the relationship would be linear. We'll see an example of a nonlinear relationship here in a second. The direction of the relationship is either positive or negative. This is mostly useful when we're talking about linear relationships because nonlinear relationships can have both directions at the same time. But a linear relationship will either have a positive direction or a negative direction, and that basically just refers to the slope of the trend line you imagine kind of going through that data. And then finally, we want to talk about the strength of the relationship. This is measured by something called the correlation, which we'll discuss here in a few minutes. But essentially, the strength of the relationship is talking about sort of the predictive power of the relationship. So, for instance, suppose I told you that an individual could make 80 hash marks in 30 seconds with their dominant hand. What would you predict about that individual's performance with their other hand? Well, if you look at our data, if the dominant hand is at 80, makes 80 hash marks, then we see a whole range of values that are possible for the other hand, ranging from, it looks like, about 50 all the way up to 75 or 80. So that would correspond to sort of moderate predictive power, right? If I tell you that someone made 80 hash marks with their dominant hand, you know something about their other hand. It probably made between 50 and 75 or 80 hash marks, but that's a pretty wide range. So the prediction isn't super accurate, and so we only say that this has moderate predictive power. And so the strength of this relationship we're looking at right here, we would describe as moderate. Again, this correlation coefficient that we'll discuss momentarily will put an actual number on that. It'll be a measurement of the strength of the relationship. So for this particular relationship, we see that we have a positive linear relationship with moderate strength. Let's look at each of these ideas in a little more detail. First, the form, linear versus nonlinear. On the left there, you see a linear relationship. This is between kind of two unrelated variables, you might think: the number of coffee shops that a town has and the number of crimes that are reported each year in that town. And what we're seeing is that as the number of coffee shops increases, so does the number of crimes. And the form of the relationship is linear. It looks like actually a pretty strong relationship as well, right? Because you can imagine a trend line going through there that would have a pretty high predictive power. On the other hand, this reminds us that just because you have an association doesn't mean there's a cause and effect relationship. I don't think anyone would seriously countenance the idea that more coffee shops cause higher crime rates. There's probably a lurking variable here, right? Uh, the uh, the real explanation is probably that larger cities have both more coffee shops and more crime. And so the relationship we see here is certainly real, but we wouldn't want to jump to the conclusion that it's a cause and effect relationships. But it is a positive linear relationship that's pretty strong. On the right, you see a very strong nonlinear relationship, right? It's a relationship between the barometric pressure and altitude in kilometers. And we see that as the altitude increases, the barometric pressure decreases, but it's not in a linear fashion. The relationship is that has a more curved kind of shape that you can see from the scatter plot. It's a very strong relationship, right? It's just not linear. It's strong though because if I tell you that, for instance, you're at an altitude of 10 kilometers, then you can see from the graph that you would predict somewhere like maybe 330 or 340 as the barometric pressure at that altitude. So a very accurate prediction could be made of barometric pressure from altitude based on that relationship, but it's a non-linear relationship because the trend just isn't a straight line. It should also be said that sometimes variables just aren't related. Here's a scatter plot of the amount of money in the emergency fund of a household versus the annual household income. And you can see that there's just no relationship at all here. Knowing the amount of money in the emergency fund in a certain household tells you almost nothing about the household income. Uh, and so you see that sort of just random blob of points in the scatter plot, and that's often indicative of a no relationship kind of situation. Now let's look at the idea of the direction of a relationship. As we said, if the relationship is a linear one, then the direction simply corresponds to the slope of the trend line you would imagine describing the relationship. So in the first case of number of coffee shops and number of crimes, we have a positive association. The second scatter plot there on the right is an association between the price of gas per gallon and presidential approval ratings on a scale of 0 to 10. And what you can see is something that is fairly understandable. As the price of gas increases, presidential approval tends to decrease. People don't like it when they have to spend a lot of money to fill up their car with gas. It's a pretty strong relationship. It's a linear relationship, and it's also a negative association because as you increase the price of gas, the presidential approval rating tends to go down. And finally, let's talk about strength. That again means the predictive power of the association. If you know, in other words, if you know the value of an individual's explanatory variable, how well can you predict the value of the response variable? The correlation coefficient, R, will measure the strength of a linear association. And you see below there 4 graphs showing various kinds of relationships and the associated correlation coefficient. The first relationship is a strong linear negative association, right? And it turns out that the correlation coefficient there is negative 0.99. If you look at the graph on the far right, you see a fairly weak positive linear association, and its correlation coefficient is R equal positive 0.5. That's one of the properties of the correlation coefficient. The sign of R, positive or negative, will tell you the direction of the linear association that you're looking at. And so the two scatter plots in between are kind of intermediate steps. The second one from the left, the moderate negative linear association, has a correlation value of negative 0.7. So again, the negative sign, indicates a negative association. And the third one from the left has a correlation coefficient of 0. And that is indicative of no linear relationship. And so correlation measures the strength of a relationship, and the sign of the correlation coefficient gives you the direction of the linear relationship. Let me run down just a few facts about correlation to get us started, and we'll look at more of these in a subsequent video. But again, correlation measures the strength of a linear relationship. If the association is nonlinear, then correlation is usually not a very meaningful measurement. So correlation is really designed to measure the strength of linear relationships. And in this class, we'll be mostly concerned with linear relationships. It turns out that correlation is always between -1 and 1. That's always the case. If the correlation is positive, that means we have a positive association. If the correlation coefficient R is negative, that means we have a negative association. And if the correlation coefficient is 0, that means we have really no linear association. Although you may have some other kind of association. So don't confuse R equals 0 of meaning that there's no association whatsoever. It just means there's no linear association. As we said, correlation is always between -1 and 1, and at those extreme values of +1 or -1, correlation has some special meanings. If the correlation is exactly 1, that means the data have a perfect positive association. That means that the data points are all going to lie along a perfect straight line with positive slope. That rarely happens in the real world, but if it does, you'll get a correlation coefficient of +1. A correlation coefficient of -1 means that you've got a perfect negative association. Your scatter plot will form a perfect straight line with a negative slope. And again, that doesn't happen often, but when it does, you'll have a correlation of -1. And so correlation of 0 means there's no linear association. A correlation of ±1 means there's a perfect positive or negative association. What about in between values? Well, the closer the correlation is to ±1, the stronger the linear association is the basic idea there. So correlation values of like 0.9 or -0.8 indicate pretty strong linear associations. Correlation values of like 0.5 or 0.3 or 0.1 or -0.5, -0.1, and so on. Those indicate moderate to weak associations, and the correlation coefficient is precisely a measure of sort of the strength. The closer the correlation coefficient is to either +1 or -1, the stronger the relationship. So that is a quick little introduction to some of the concepts associated with linear regression. We'll be diving deep into more of these as we make our way forward through this material. So stay tuned, stay safe, and we'll be talking at you again real soon.